Oh, yeah, thanks. Yeah. Talk about two other, let's say, important algorithms. And the first one is going to be the, well, this doesn't need, the quantum Fourier transform. And then we will see of this an application that is called phase estimation, I think. And then the second one is well known, is the Grover algorithm. Now, the idea is that today we are going to do this, and maybe we can begin a little bit this, and tomorrow we are going to finish the Grover, and we will do some application of the Grover algorithm that are quite nice. And there will be essentially some, let's say that tomorrow will be essentially some exercise session based on the Grover algorithm. So let's start with this. And let's start by recalling the classical version. So let's talk about, let's say, first classical Fourier transform, not to be confused with field theory. And the classical Fourier transform, we will, let's say, I think whenever you talk about computational problems and so on, the Fourier transform that we consider is the discrete version, so the discrete Fourier transform. So let's start by recalling what is this, this guy classically. So essentially, the DFT, it's just n by n matrix that we call Fn, such that these two properties are satisfied. Fn is unitary, and let's say Fn component AB modulo square is equal to 1 for each A, B in 0 and minus 1. Okay? So this is essentially what a Fourier transform is in the discrete in the discrete world, let's say. And for example, what is F2? So we need a 2 by 2 matrix, which is unitary, and each component have modulus 1. Any candidate? Almost. Eh? Almost. No, come on, okay. I mean, it's the Hadamard gate, right? Which is, if you want, it's identity plus Z, right? So you were not so far. It was a Pauli plus something else with the square root of 2. Why? Well, we get 1 over square root of 2, 1, 1, 1, minus 1. The Pauli is not good because you don't satisfy this per se. You have components that are 0. So you need to put this. And this, of course, satisfies, right? The vectors are orthogonal to each other, so they form a unitary matrix, and each component has, let's say, this as norm 1. Yes? I mean, then you normalize, but yeah, yeah, here there is an inconsistency, I'm realizing right now. Yeah, here there is an inconsistency. Well, okay, forget about the inconsistency, just, I mean, this must be normalized, so this is probably 1 over square root of n. Yes, I would say 1 over square root of n, such that this is satisfied, otherwise it's inconsistent. Anyway, this is the matrix. Now, what we can do if we want to go to larger n, well, it's very easy to realize that you cannot do it with the real numbers, so you have to play with a complex number. And the strategy, let's say the prescription is very simple. If n is larger than 2, what we have to do is to define the n root of unity, which is omega n equal to e to the 2 pi I over n, right? And then we can define fn component jk equal to 1 over square root of n omega n to the power times j times k. So let's say more explicitly, if you want, this becomes 1 over square root of n e to the 2 pi I over n j k. So here probably you start to see something, let's say, more, I mean, you start to see the formula that we are used to when we do continuous Fourier transform, right? This is the discrete version, but it's exactly the same thing. So as a matrix, we get a big 1 over square root of n in front, and then the jk location is characterized by omega n jk. So once we have defined this object, then we can compute, let's say, the real discrete Fourier transform. It's a map that, if you want, takes a vector Vn and map it to V, let's say, capital N, which is simply Fn Vn, right? And okay, let's say explicitly, it's a triviality. Vn component j is equal to 1 over square root of 1 over square root of n summation over k omega n to the power j times k Vn component k. Okay, so this is our formula. Okay, so classically, what is the complexity of this algorithm? I mean, not complexity in terms of calling an oracle. This is an algorithm that is not realized in terms of an oracle, but let's say how many, let's say, fundamental operations, so how many small sum and small product you have to do here. N square, exactly. So the complexity of this algorithm is O(n) square. However, somebody could have heard about the so-called fast Fourier transform, right? Which is given as an exercise. It's probably problem 15, so take it as an exercise. But let's say, implementing this fast Fourier transform, we can, let's say, reduce this complexity to O(n) log n. So you, let's say, reduce the complexity by going down to linear times a logarithm that in this business is essentially nothing. So the complexity is almost linear. And if you want to make an experiment, you can write a simple code like this that use the Orange square. Then you can use a fast Fourier transform implementation, and you can see that as soon as the matrix start to be large enough, the difference in performance is astonishing. So it's a great improvement. So this is fast Fourier transform. And as I said, it's given as an exercise, so I leave it for the moment. Questions or comments or complaints? Okay, good. Well, because let's say for each component J, right, you need to, let's say, multiply and then sum together n numbers, right? And then you have to redo for all the components that are other J, so n square. Other? Yeah. I would say yes, no? Am I wrong? No, sorry, no, sorry, thanks. X, thanks, yeah. So it was even closer, right? It was almost, is it correct now or wrong? No, it's correct, yeah. Okay, yeah, thanks. So we were really close, eh? We were saying Pauli almost, I mean, it was a linear combination. Yeah, indeed. You can always claim, I wanted to say linear combination. Yes. Okay, good. Good, so now let's move to the quantum case. So now, clearly, the fact that this is unitary is already telling us that, by the way, again, let's assume for, I mean, just for being practical, that as usual, we like even numbers and we like powers of 2. So let's assume that n is a power of 2. Now, in the quantum case, I mean, the fact that Fn is unitary it's essentially telling us that this is already per se a quantum operation. So if you want, Fn already define an operation acting on psi, which is an n-qubit state, and so this can go to, what I write, psi at, which is given by Fn acting on psi. So if you want, Fn is already per se quantum operation because it's unitary. So I mean, it's linear for obvious reason, and it is unitary. So it's a quantum operation. So our goal is to, so again, this is a little bit of orthogonal to what we did yesterday. So we are gonna, so our goal now is to look for an efficient circuit that realize this operation. So we will really, let's say, draw the circuit at the end. We will not work with oracles. We will work at the low level, if you want, for the Fourier transform. And okay, one could, let's say, naively, say that you want to beat this, right? You want to find a circuit that implements the Fourier transform with a number of operations, or if you want, a number of gates that is smaller than this. However, this is a bit naive as an approach. Somebody has an idea why it's naive? So let me recap. You want to transform this guy to this guy with a circuit, and now comes the naive part. I want that my circuit runs, let's say, as a complexity that is below n log n. However, as I said, this is a naive And if you want, it's a bit cheating in favor of quantum. So it's, I mean, if you want to advocate that quantum is good, of course, it's a good way, but it's a bit unfair with the classical counterpart. Somebody has an idea? Okay, it's a little bit on the line of what we discussed yesterday about quantum parallelism. This rings a bell to somebody? No, okay. I mean, at least you remember about quantum parallelism, right? Okay, yes, okay, that is already good. So, if you want, in the classical transformation, what you do is to take one vector that somehow is written on paper, and you build another vector that somehow is written on paper. So you build 2 to the n numbers, if you want, out of this operation. Here, you are doing something different. Is this now ringing a bell? No, well, why n plus 1? I would say n, small n. Small n. No, that was not my idea. My idea was that once you have done this operation, you have a bunch of amplitudes that follow, if you want, this rule. So you have n, big N, big N amplitudes. But they are not written on paper. You have at a certain moment to make a measurement, and that creates the usual collapse. So it's a little bit unfair because the comparison is between something that you can look and use and something that is living in a superposition that you have to make use of in an accurate way. So it's a little bit like yesterday when we were getting excited about quantum parallelism, but then we realized that what we were really doing was just a randomization of a classical function. So we will see that this is a very powerful algorithm, but pretending that beating this complexity means a quantum advantage is a little bit cheating. Okay. It depends. It's like we saw yesterday. We during the DOIS, if you want, we did quantum parallelism and we saw something beautiful but useless. Then we did Bernstein-Vasirani or Deutsch-Josva, and we saw a beautiful application of that useless idea. So it depends on you. The idea is that you do a Fourier transform, you get a superposition with some properties. The properties are dictated by this, and then it's up to your creativity and smartness to make good use of that state. So if you directly measure, you don't do anything useful. If you do something better, maybe yes. Almost. In a sense, yes. Indeed, okay, good point. Yes, this is a sort of halfway in the sense that the Fourier transform, it's, in a sense, a subroutine in a larger algorithm, in general. Nobody used the Fourier transform per se, I would say. You use as a subroutine in a larger algorithm. Good. Other comments or questions? Good. Okay, so now we want to go to the quantum circuit, as I said. So we want to go here. And okay, let's define a little bit the rules of our game. So let's see what kind of circuits, let's say what kind of gates we will allow. And we will allow this that I call RS gates, which are 1 qubit gate that goes like 1, 0, 0, e to the 2 pi I divided 2 to the s. So in particular, suppose that I take R1. This is what? Almost. Z. Who said Z? Good. Because you get -1, right? So you get 1, -1, 0, 0. So this is a Z gate. A NOT gate is here. And it is 1, 1. Okay, good. Good, so this is 1. And okay, we will promote as usual, and this guy to be CRS. So we will become, this will become a control qubit, control operation, acting then on 2 qubits, in which when you do the operation will be RS. And this use, if you did some exercise, there is a well-defined prescription in order to promote a 1 qubit unitary to a control version, right? Yeah. Okay, so we will allow this guy, and we will allow the Hadamard gates. And also we will allow, but we'll arrive just at the end, some swap gates. So these are our ingredients. This, and this. Good? By the way, the swap, if you did the exercise, is just a bunch of C nodes. Okay, now, by the way, notice, if suppose that S is very large, what is this gate? Exactly, so identity. So let's say when S become to infinity, RS is almost the identity. And you can make this claim precise. I didn't give it as an exercise because I find it tedious. But you can show that, let's say, the quality of the circuit doesn't, remain good by killing, if you want, all the RS for S that are large enough. So this is something that in practice is useful. Because you don't, having an identity, you don't do nothing. You do nothing, so you can, let's say, reduce the complexity further by this trick. Good. So let's compute. So now our goal is to compute, let's say, to understand well how Fn act, and then build a circuit that use these ingredients. So we can make use of a nice property of quantum mechanics, which is linearity, right? So the idea is that the only thing that we really need in order to compute, in order to characterize this operation, is to compute Fn acting on K, where, let's say, K can be, if you want K, it's equal to, how do I write? Yes. K1, Kn, with, if you want, Ki equal to 0 or 1. Right? You can do on this, and this enough. By the way, remember, we will use, let's say, a convention in which this guy is the most significant bit, which means it's the largest. So if you want, this guy goes like 2 to the n, or n minus 1. All the time I got confused. Well, something like that. And this guy will go like 2 to the 0. Okay, so probably this is 2 to the n minus 1. Okay, fine. Good. Okay, and now we need also an extra, let's say, small property. Let's assume that we have in base 2. So again, let me specify that we are in base 2. And let's assume that we have a J such that, once again, can be written like J1, Jn. Now, we want a formula for 0.J1, J1, Jn. This, let's see if everybody agree, this can be written as J divided by 2 to the n. You agree? It's like, once we go to base 2, what is typically done by 10 is done by 2. So you move the zeros with powers of 2. So this is this. And so this can be written as J1 times 2 to the n minus 1 plus, plus Jn 2 to the 0, everything 1 over 2 to the n, and so finally we obtain this formula, summation L from 1 to n of j L 2 to the minus L. That j divided by 2 to the n can be written in this form, in which the first digit, if you want, become to the power 2 to the minus 1, and so on and so forth. It's a pretty simple formula. Good. So now we are ready to compute Fnk, and I will probably move there. Yeah. Let's do an example. So, for example, suppose that k is equal to 1, 0, 1. This becomes 2 times 2 to the 2 plus 0 times 2 to the 1 plus 1 2 to the power 2 to the 0. So this becomes 5. And this is the most significant in the sense that it's the largest. So I'm saying significant in the sense of significant digits, like, yeah. Okay, so now Fn acting on k, let's compute. So this becomes 1 over square root of n summation j from 0 to n minus 1 exponential of 2 to the pi I j k divided by 2n acting on j. Yeah, this is the first step in which I simply applied the formula, nothing more, nothing less than that. Yes. Then this becomes 1 over square root of 2n summation j for all the possible j's, so j from, let's say, belonging to 0, 1 to the n, and here this becomes exponential of 2 pi I summation L from 1 to n j L 2 to the minus L times k acting on j1 jn. Here I'm simply applying that formula to this, if you want. Okay? Then I go forward, and this becomes 1 over, I mean, the formula looks ugly, but the final point will be nice, so be patient. 1 over 2 to the power of 2, 1 over square root of 2n, summation over all the possible j belonging to 0, 1 to the power of n. The exponential, what I'm doing here, yes. Yes. Wait, no, indeed. I want to promote this sum to a product, so this becomes product over all the L from 1 to n, e to the 2 pi I j digit L divided by 2 to the L times k, acting once again on my J1, Jn. And now the magic is that I can exchange essentially these two, and I got this nice formula, which is simply the tensor product for L that goes from 1 to n of this beast. Well, I put in front 1 over square root of 2. Zero plus e to the 2 pi I k divided by 2 to the L acting on 1. So we started with the Fourier transform acting on a product state, and we end up on another product state. So we see that on basis vectors, the Fourier transform doesn't create an entanglement, which is good, because will allow us to compute the, let's say, to draw the circuit in a much easier way. Questions? Okay. So now we just need to massage a little bit more this guy. So let's write a little bit more this guy. So we have the exponential of 2 pi I k over 2 to the L, right? This can be written as the exponential of 2 pi I, 2 pi I times, and here we have k1 up to k n minus L dot like dot, I don't know how to say, n minus L plus 1 k n. So in other words, dividing by 2 to the L is telling us that this k, that was a string of k1, k2, up to kn, put a dot in position L, if you want. Right? Or better. I mean, from here, you start to go back, you do L steps, and you put the dot, because this is the less significant digit. Now, why this is nice? Because all the digits appearing here are, yeah? Sorry, can you repeat? The subscript of the last, this, Jn. No, yeah, sorry, this is JL. It's not capital. JL, yes. Ah, yeah, sorry, it's bad written, okay. Yeah, sorry, it's still bad written, probably, but okay. You got it. Okay, so why this is nice? Well, because if you want, all these digits are part of an integer, right? So x to the 2 pi I, an integer, is nothing, is 1. So we can forget about this. And so finally we learn that this guy becomes exponential of 2 pi I, 0 dot, and we have k n minus L plus 1 up to k n. And notice that now we start to arrive at the right spot, because we start to see something very similar to this guy that we were looking for. So this is, if you want, the end of the story, because we have, by linearity, we have completely done with our problem. We have the Fourier transform over all the possible basis vectors, which take this form, like a superposition of 0 and 1, with a phase factor, a relative phase factor, that is likely well controlled by some gates like that. So now we are ready for an example such that we can figure out the general recipe. Okay, is it clear? Yes. No. Ah, the zero you don't, because if you want, this is like to say, okay, let's work with, because we are human, so let's work with 10, with base 10. I mean, it's the same, logically it's the same thing. If you want to compute exp 2 pi I 5 times 5.3, do you agree that this is exactly the same of exp 2 pi I times 0.3? Is exactly that. It's exactly that, but it's just in base 2. But it's exactly the same thing. Everything that is integer multiplied by 2 pi makes an integer 2 pi, and so is 1. Other? Okay. So let's do the example. So now we have the formula, so let's do an example. Let's consider the case n equal to 3, which means n equal to 8. So we know that F8 acting on K1, K2, and K3, using this formula, become 1 over square root of 2, 0, plus e to the 2 pi I 0 dot K3 acting on 1, because when I put L, wait, where is? Yes, on K3 I have the less significant digit, which is K3, and so that means that I have n minus, no, what I'm doing, sorry. I'm here. To do the 2 pi k over 2 to the L, yes, so if I put 2 to the L equal to 1, this become 2, and so I have K1, K2, and K3. K1 and K2 doesn't matter because go before the comma, and so only K3 remain. So this is the first tensor, 1 over square root of 2, 0 plus e to the 2 pi I 0 dot K3, K2, 1, tensor, 1 over square root of 2, 0 plus e to the 2 pi I 0 dot, sorry, this is the other way around, K2, K3, 0 dot K1, K2, K3, acting on 1. So this is our state, right? For 3 qubits. Now the circuit becomes quite easy to draw. So let's start with this that is the simplest. So let's say, suppose that K3 is equal to 0. This becomes 0 plus e to the 2 pi I 0, which is 1. So become simply 0 plus 1. So K3 equal to 0 become, let's say, 0 plus 1. divided by square root of 2. Now let's assume that this is instead 1, so it becomes 2 pi I 0.1, which means 2 to the minus 1, so this cancel, and so this becomes a minus sign. So if K3 is equal to 1, we get 0 minus 1. So we see, right, that this guy can be reproduced by a simple Hadamard gate. If K3, so if you want, can act on this guy, on K3, acting in Hadamard, and you reproduce this guy. So we have, if you want, the first point is that K3 evolve, receive an Hadamard, and goes. Now let's see K2. Well, K2 will have, at this level, for the first digit, we'll have exactly the same behavior of this. So we have to put an Hadamard here. And then we have to put some RS with S equal to 2, because this guy is going to act here. So we need an R2. But this R2 must be applied depending on K3. So in order to do this guy, we have to do something like, let's say, control with this guy before acting the Hadamard, of course, because this is related to the initial state of K3. Before, we have to put, an R2. And then, actually it was the other way around, sorry. Okay, let's redo the draw. Okay, so let's finish. First, let's say what is going to happen. So we have an R2 controlled by K3. And here we need to have an Hadamard, then an R2 controlled by K2, once again, and then an R3 controlled by K3. So let's try to draw, and then we comment. So my claim is that this is almost the right circuit. H, R2, R3, so here we need to put the control here. Then here we put our H. And here we put the R2. And here we start. At this level, we apply the control, and we go here. At this level, we apply the control, and then we put our H. Now so this is the circuit, almost. So we see that, let's say, for this state, K3, we just do the Hadamard. For this state, we first do the Hadamard, and then we do the R2 if K3 was different. And here we do the Hadamard, then the R2 if K2 is 1, and we do the R3 if also K3 is equal to 1. It's almost this, but with a problem. Yes, okay, so let's restart. So here you see that there is a qubit that, depending on the initial value of K3, must, let's say, put a plus sign or a minus sign. So this is definitely an Hadamard acting on K3, right? Then here, you see that depending on K2, you must have a plus or a minus, and then you have to put a rotation at the second digit, depending on the value of K3. This, you have to do an operation like this. Let's call it, it's not a rotation, right. Okay, so you have to play with this guy when this guy, with this guy equal to 2, such that you have 2 to the 2 pi over 2 minus, if you want, if you put s equal to 2, this become e to the 2 pi I 1 divided 2 minus 2, 2 to the minus 2, which is e to the 2 pi I 0.01. Because you want the rotation at the second digit, right? We said, let's call it rotation. The operation RS at the first digit is just an Hadamard operation. At the second digit become this operation, and to go to the second digit, you have to put 2 to the 2. Then let's see the last one. The last one has to do an Hadamard, then has to do a rotation at the second digit if K2 was different than 1, was equal to 1, and then a rotation at the third digit if K3 is equal to 1. So let's see, here there is a Hadamard, here there is the Hadamard, and then the rotation controlled by the value of K3. Notice that it's crucial that you put this here and not here, because here you don't have any more K3. And then, with the same logic, you have this. Is it clear? For you, yes. For you, yes. Somebody there? Okay, they prefer to avoid to answer. Now, it's almost done, right? Somebody can see what is still wrong? What is this guy? It's the first qubit, right? And we're putting here. And this is the last qubit. And we're putting here. So we need to put a swap gate between these two. Now, the general recipe, suppose that we want to add an extra, with an abuse of notation, we want to add, well, let's use the yellow one. We want to add an extra, let's say, K0. This guy will have to receive immediately an Hadamard, right? Then we'll have to receive an R2 here before the Hadamard, then an R3 here before the Hadamard, and then an R4 here before the Hadamard. Then we will have to do all the swap, and in this case, the swap will be between this and this and this and this. And we can do iteratively in the same way. Yes, so this is the way to construct the Fourier transform. Now, what is the complexity? Well, the beauty of the big O notation is that we don't care much about details. So let's take the worst possible case. The worst possible case is the most significant guy here. This guy receives a number of operations that is proportional to the number of qubits, right? So let's be very brutal. We can say that the complexity of this guy is of order n, where n is the number of qubits, n squared. Assuming, which is wrong, that all the other receive, I mean, this is an upper bound, so when you have upper bound, you can be brutal. So you can say, okay, at most, each qubit receive n operation. Let's say that the complexity is on O(n) squared. Of course, it's smaller than that. But and comparing with this, this was of order 2 to the n log, let's say 2 to the n. So we could claim that there is an exponential advantage, but we are cheating for the reason that we said, in the sense that we are doing two different operations. In one case, we really compute something. In this case, we are preparing a state, and then there will be something else to do. Okay, how many are still alive? Okay, you are. Okay, good. You are not, right? No, you are not. Okay, we can maybe we can. I mean, how many are completely lost at this stage? 1, 2, 3. Many. Okay, so let's take a break here. What is? I mean, I use him because he's close as an ambassador, let's say. So he's gonna talk for everybody. Just because he's closer. It's not that I'm making preferences. So what is that is making you completely confused? Until here? No. Okay. So here we have K1, K2, blah, blah, up to Kn, right? So this guy is K1, K2, up to Kn. Now, question. If I give you in our beloved base 10, I give you 8, 7, 6, 5, 1, 2, divided by 10 to the 2. Do you have to suffer, or you know where to put the dot? This is exactly the same thing. You have to put the dot after L digits coming from the right. So you count, and the digit arrive, the dot arrive exactly here. Is exactly the same thing. Unfortunately, we have 2 fingers instead of 2. We have 10 fingers instead of 2. So we are used to base 10 rather than base 2, but it's exactly the same thing. Good. Now we go back to his question. Suppose, again, let's work in base 10 because we are used to. Suppose that you are asked to compute exp of 2 pi I times, this is not a dot in the sense of scalar product, it's just a time, 5.6. Do we agree that this is exactly the same of exp 2 pi I times 0.6? Yeah, no, because if you multiply 2 pi I by an integer number of time, you are essentially rotating in the trigonometrical circle 5 times. And so you go back to the initial point. Good? Okay, so this is done. So now you're happy? Okay, so here I just wrote this expression. Right. Then I recognize there is 1 qubit that has to receive this sort of treatment. So must become 0 plus 1 in case K3 is equal to 0. Or 0 minus 1 in case K3 is equal to 1. Okay, and I know that this is done by a Hadamard gate. Good. So I start to draw this line because it's the simplest. Well, because here you have to receive other stuff. This guy just received this stuff. And of course, you have to put it here because its evolution, if you want, its fate, it's here, depends on the status of K3. So you have to put it there. Then you go to the second simplest. And you see that at the first digit, you are doing exactly the same that you were doing here. But this time, if you want, control is not the proper way, but more or less control by the status of K2. If K2 is equal to 1, you have to put a minus sign. If K2 is equal to 0, you don't have to put. So you put an Hadamard gate. Then you have to do this rotation at the second digit. Now, if you understood there, you see that if you want 2 pi I time 0.01 is obtained by putting here 2. Good. So you have to do an R2, but again, the status of the R2, it will be controlled by the third qubit. So you have to do a control R2 rotation, R2 operation. And then, if you understood, now we are almost ready. Here you have to do Hadamard, then the R2 controlled by the second qubit, and then finally the R3 this time, because you have to go 3 digits if you want, so you need an R3 controlled by the K3 qubit. And so this. Now you arrived here, almost finished, but you recognize that now you have that the first qubit that should receive this treatment is actually receiving this treatment. And this qubit is receiving the right treatment. And this qubit that should receive this treatment is receiving this. You swap the two. Now, people, your ambassador did a good job? Yes. Okay, good. Mm-hmm. No, just because we are lazy. So we say, okay, in the worst case scenario, we do n operations. And let's assume, I mean, you know, when we use the big O notation, we are putting an upper bound. So we can say that the complexity is upper bounded by n squared. Why? Because in the worst case, you do n operation. All the others are doing less than n. And so let's say that you do n operation times n qubit. You are, I mean, okay. It's not n factorial, by the way. It will be n plus n minus 1 plus, but with a plus, not with the product. So it's much lower than. But you are, let's say, when you do upper bound, you don't care about details. So you say, okay, n squared. Of course, if somebody arrive and say, oh, I have complexity, oh, n 1.75, if you want to beat your competitor, you have to count properly and see. But if you want to beat this bad bound, n squared is already enough to pretend that you are doing something exponentially better. Even though, as we said, in principle, there is a cheating over there. Well, they were here, right, from the beginning. Then we massaged the expression in order to arrive to something more manageable. But they were there. Other? You are complaining here? Okay. Good. So let's see. So this guy, suppose K3, is here. Suppose K3 is equal to 0, right? So this becomes 0 plus e to the 2 pi I 0, which is 1. This. Then you do K3 equal to 1, you do 0 plus e to the 2 pi I 0.1. But we are in base 2, we have 2 fingers. So this is actually 2 to the minus 1. Right? So 1 over 2, 2 cancel this, and you remain with pi I. Yeah, it's a pity that computer science use 2 fingers instead of 10. I mean, makes life sad, but yeah. Okay. Well, in principle, the time is over, almost. I wanted to do also the phase estimation, Do you want to suffer 5 minutes more and see the phase estimation? Yes, okay. Okay, even the ambassador, so yes, so we are. Okay, so let's see an application now. Okay, so, no, this is the wrong paper. So should be here, yes. So now the problem. So suppose that we have a unitary U, and we have, so we have U, and we have one of its eigenvector psi. So that means that U acting on psi is equal to lambda psi, right? And we know, since this is unitary, that this guy can be written as e to the 2 pi I phi with phi in 0, 1, right? So this is the status. And our goal is to estimate estimate phi. Okay, so let's assume, for simplicity, but it's not really mandatory, let's assume that phi can be written as 0 dot phi 1, phi n, so can be written in n bits precision. Again, I'm counting in base 2, so these are just 0 and 1, nothing more. Okay, so here is the algorithm. So let's start with an n plus n state, which is initialized in the state 0 to the power of n, and here we put psi. No, sorry, it's not, it's n, and then we have the state psi that is controlled by the dimension of this unitary. So can be anything, sorry. But this is n register, and it is in the state 0, 0, 0, 0, 0, all of them. Then, so this is the starting point. Then we apply h of Hadamard to the power of n over this state. So what we get is that 0 to the power of n psi become 1 over square root of 2 to the power of n, summation, I'm assuming that this has dimension capital N, j equal to 0 to, well, let's say n minus 1, where there is the usual 2 to the n. Okay, and I get j psi. Right, now I do the usual thing. We apply the Hadamard and we create all the computational basis. Now, the next thing, we apply this map. For each j psi appearing there, we do the following. J u to the power j psi. And there is an exercise asking you to show how this can be done with the circuit. Once you do that, you should be convinced that this become, this guy become e to the 2 pi I phi j psi, right? Because we are applying, phi times j. Because we are applying u to an eigenstate, each eigenstate, the eigenstate has eigenvalue 2 to the 2 pi I phi, and then you do j times, you get a j there. Good? And now, black magic, that I leave as an exercise, you realize that doing this over this state, the final state, so if you want this guy after this operation, become Fn 2n phi psi. This is an exercise. In other words, you apply this operation over all the members here. You do a bit of massage on this expression, and you recognize that this can be written in this form. And now you simply apply an inverse Fourier transform to end up with the state 2 to the power of n phi psi, which means you get 2 to the power of n of phi with the assumption that phi could be written in this way. You end up with phi 1, phi n, psi. You do a measurement in the computational basis, you have reconstruct your eigenvalues. So this is called phase estimation because you can use essentially a Fourier transform, an inverse Fourier transform, but it's essentially the same thing. And you reconstruct a phase with precision that you want by building, by doing this operation. So if you want, the exercises are to build a circuit that do this operation, and then show that the resulting state is actually the same of this, such that then you do an inverse Fourier transform and you end up here. Okay, we are over time, so yeah, let's stop here. We had an intensive question session during the lecture, so okay. This is probably the reason.
Thank you for your class. Can you explain again what is necessary to change the finally qubits in the...
Yeah. Unfortunately, I erased, but hopefully you still have it. So we were saying that the Fourier transform of K1, K2, K3 was this, this, this. Now, when you draw the circuit, you realize that in the first position, there is something that is actually here in the third position. And at the same time, in the first position, there is something that should be here. So you have to swap the two. If you have 4 qubits, you would realize that here you have what should be here you have what should be here, and here again. So you have to swap this with this and this with this. So in general, you have to do all these swaps between, let's say, far right, far left, a little bit more left, a little bit more right, and so on and so forth until you close the thing.
Other questions? Okay, so let's thank Dario again.